So the discussion this afternoon is we're going to talk about part of the functional safety life cycle. So to give a little bit of context here, we're talking about the standards, international standards, which cover automated protection systems that are designed into high hazard facilities such as oil refineries and offshore oil and gas facilities, and also useful for machinery applications, medical applications, transport applications, and so on. We'll be focused particularly in our examples on the process industry, so for example oil and gas, petrochemical, those kinds of application. The relevant standards we're talking about here are IEC 61508 and 61511, and those standards define a cycle of activities that's necessary to achieve a high degree of reliability for these automatic shutdown systems. And that cycle is referred to as the functional safety life cycle. Now, part of the life cycle involves performing various checks to make sure that activities, especially during the design phase of the life cycle, have been performed correctly. And there are two main well, there are actually several different kinds of checks, but two of them that we're going to talk about today are referred to as verification and validation. And if you're familiar with other kinds of, for example, quality management systems like ISO 9000, you might well have already heard these terms used in the context of that standard. And these are somewhat similar, but we're going to focus particularly on the functional safety usage of the terms verification and validation today. So the slide that I'm hoping you can see on your screen at the moment shows you what I'm going to cover. First of all, I'm going to talk what is the point of verification and validation. Secondly, how do we actually do them? And thirdly, how do they fit into the overall functional safety life cycle? In other words, when should we do them? How can we do them effectively? Who should do them? And how can we get the best value out of them? And then finally, I'm going to try to show how we can do them efficiently. It's like all activities to do with these kinds of safety system, they can consume a lot of time and resources, and not necessarily give the maximum benefit unless we do it efficiently. So I'll be talking a little bit about how to achieve that. So let's start off by thinking about why we even need to do checks. Well, we do checks because systems can fail, including these automatic safety systems. So what kinds of failures are we interested in? Well, normally we divide up the possible failures that we're concerned about into two general types, which we refer to as random failures and systematic failures. Now, random failures are essentially hardware malfunctions. This would be if we have some item of hardware which is operating within its design parameters and within its useful life. So if it has, for example, a useful life of 10 years, it hasn't been in service for 10 years, and it's within its parameters of temperature and humidity and operating voltage and operating environment and all the rest of it. Even so, sometimes devices will fail. And those failures are predictable in the sense that we know an expected failure rate for those events based on statistics. And we can use that to calculate an expected probability that the safety system that includes that device will not perform its task when it needs to perform its task. So random failures, to some extent, we can take account of them mathematically, and we can design our system to be robust enough that the probability of failure is acceptably low. So much for random failures, but what about the other kind of failure, systematic failures? Well, systematic failures are basically when we have some kind of human error which leads to a chain of events, and eventually the end result of which is the safety system can't do its job. Now, that chain of events might actually go on for years. It could be that somebody makes a design fault, introduces a design fault today, which doesn't reveal itself until 10 years later. And then, of course, it can be very difficult to trace back. Now, the problem with anything to do with errors by humans is it's extremely hard to predict what kind of errors will be made, when they will be made, how often they will be made, and how serious they would be. There are some mathematical models we can use, but they're nowhere near as robust or as sound yet as the mathematical models we have for random failures. So for the control and management of systematic failures, we tend not to rely on maths and trying to get them down to an acceptable level. What we do instead is we try to use strategies to minimize the chance of faults that can lead to systematic failures being designed in and then left in undiscovered in the system. And in other words, as it says on your screen, we cannot predict them, we cannot control them. The only thing we can do is minimize them. Now, how do we do that? We have only one way, and that is procedures. We need to write procedures, we need to formally review and approve procedures, and we need to follow them, and we need to demonstrate that procedures are being followed. Now, the point of verification and validation, which we're talking about here today, is to confirm that procedures are being followed. And we're going to show in a bit more detail as we go through how that works. Ideally, of course, we want to not make mistakes in the first place. And that's part of the purpose of why we have procedures. It's to help people to work in an error-free way. However, despite our best efforts, mistakes will be made. And verification and validation are designed to catch errors that have been made after the fact, after the error has already been made. Verification and validation approach the task of trapping errors in two different ways. Verification is performed all the way through the life cycle. So every time we perform a life cycle activity, we are supposed to verify that activity as a standalone activity. So that should be done repeatedly. Of course, not the same scope over and over again, but each individual part of the scope, of the life cycle scope, or each individual task to be verified one after the other at the time that we perform the task. Validation, however, is a totally different activity. Validation is a one-time check, which basically is done at the end of the commissioning activity. And it's our last chance to catch any remaining issues before we actually switch on and introduce the hazard that the safety system is designed to control. So it's really a completely different activity, and one of the reasons I wanted to do this webinar on this topic is there's often confusion. People tend to group them together, verification and validation, V and V we call it, but actually they are really different, and we need to make sure we clearly understand the differences. So hopefully by the end of this session the differences will be clear to us all. One thing I'd like to mention is quite often if we have a robust system especially for verification, it's easy to allow ourselves to become over-dependent on it. For example, if I'm writing, let's say I'm writing a procedure, or let's say I've done a HAZOP study and I'm writing the HAZOP report. So maybe I'm feeling tired, maybe I'm feeling lazy. I just write the HAZOP report and it seems good enough to me, and I'm not too worried about it being absolutely right because I know somebody else is going to check afterwards. Now that is a disaster, because what I've essentially done there is I've lost a layer of protection. You're probably familiar with the concept of layers of protection, especially if you've done LOPA study or HAZOP study. The idea is that each layer of protection is able to trap a large proportion of the failures or the situations that come its way. However, if I write my HAZOP report in a lazy way and then rely on my verifier or my reviewer to find all the errors that I've made, then it's almost as if there's no review at all. We've turned two layers of protection into only one layer of protection. So we must stress to all our people that the verification is a backup. It's not meant to be the main way of finding and trapping and minimizing errors. And people should still be, how should we say, politely reminded that they must do their work right first time and not rely on checkers to find the faults. Okay, now I've got that little issue out of my system. Let's move on and see how, in a little bit more detail, how do verification and validation fit into the safety life cycle. What you can see here is a very, very compact view of the life cycle. It shows the three main parts of the life cycle. We have green at the top, which is the risk analysis phase. We have the yellow section in the middle, which is the implementation phase, where we actually take a specification that we've developed in the green phase and we build a safety system to that specification. And then we moved into the third section, which is the operational part, the operational lifetime when the hazard is present, and that's the red part at the bottom. Now there's lots and lots of detail missing out of this. It's just meant to give a very quick overview. And the major point I want to make here is look on the left side of the screen. You can see verification happening at every individual phase of the life cycle, and that's how it's supposed to work. We do it, we verify it. We do it, we verify it. Step by step, one by one. And really we should not proceed through the life cycle from step to step until each step before has been successfully verified. That's really how it should work. On the right side of the image, you can see where the validation fits in. And it comes in towards the end of the commissioning phase. Now you can also see another little bubble on the right side, which is labeled Stage 3 FSA or PSSR. Now FSA is Functional Safety Assessment. Stage 3 refers to the fact that in the IEC 61511 standard, it recommends that you perform a task called Functional Safety Assessment at 5 different points in the safety life cycle. However, only one of those is compulsory, and that one is the Stage 3, which occurs immediately after the validation. So it's practically the last thing you do during the implementation, the yellow phase of the safety life cycle, as I've drawn it here. And validation is an input to the FSA. So one of the things you will do in the FSA assessment is confirm, has the validation been performed? Is it complete? Are all of the issues that it raised successfully closed out? PSSR stands for Pre-Startup Safety Review. And this is an alternative name that some companies and some industries use, and it essentially means the same thing as functional safety assessment. Good, so now we see how verification and validation fit into the life cycle. I want to mention one special case. We are familiar, I think many of us, with a particular activity that's performed during the safety life cycle, which is often called SIL verification. Now, SIL verification, it's got the word verification in the name, so how is it related to the verification that we're talking about today? Well, it is a verification activity. It's the verification that the conceptual design, which is the first phase of the yellow part, the implementation part of the life cycle, has been successfully completed. But the reason why we tend to treat this one rather differently from other verification activities is that it's much more specialized. It needs specialized skills, you need a lot of data, failure rate data especially, to perform it. And you usually need specialized software to do the calculations. It is possible to do it without fancy software, but it's an awful lot easier with the dedicated software. So today we'll not really be talking about SIL verification specifically. We're going to talk about the concept of verification of each safety lifecycle step more generally. If you want to know more about SIL verification, of course, we're only too happy to advise you on that. Do feel free to get in touch with us afterwards and we'll help you with that. Right, now let's focus in on verification itself. How does it work? What do we do to achieve a successful verification of one phase? Well, verification focuses on one phase at a time. It's a review of the work done in that one phase. And specifically, the purpose of verification is to look at the inputs to that phase and look at the procedure that was supposed to be used to execute that phase. Now, the inputs combined with the procedure should generate a specific output. And in an ideal world, the output you get would be independent of who performs the life cycle step. In practice, it's never quite going to be like that because there's always some subjective element, especially in risk analysis phase, for example. But in general, it should be possible to see that if I use these inputs and this procedure, I should expect to get this output. And we do this phase by phase, one by one, as soon as the work is done for each phase. Now, clearly, in order to do this verification activity, we need to know what to expect. So we need to know what inputs are coming in, we need to know what procedure should be followed, and we need to know what outputs to expect. Now, some quite useful guidance is given to us concerning this in IEC 61508. There's a very nice table at the beginning of part 1 that lists out all of the recommended safety lifecycle phases with expected inputs, talks a little bit about the procedure and the expected outputs. So that's a good place to start, a table like that. Normally, the way this is handled is you would have a table, something like that, in your functional safety management plan, without which you shouldn't even be starting your functional safety lifecycle activities. So the functional safety management plan is a key part of what we're talking about here, and that's where these kind of basic building blocks of the verification should have been defined. But the other thing you can see there is, of course, it means that for each phase of the life cycle, we need to have a very clear and very well-defined procedure. Sometimes we do have that. For example, a HAZOP or a SIL determination study will very often have a nicely defined procedure. So our verification can be a cross-check against the procedure to confirm that the procedure was followed. However, the procedure often is not written with verification in mind. And this is a point where I think there's a lot of scope for improvement in the way we do our life cycle activities. If we were to write our functional safety procedures one by one for each phase with verification in mind, we could actually do the verification activity very efficiently. It would take a very small amount of time and effort and manpower, and we would get very high return in terms of finding any errors, any important errors. I'm not talking about trivial stuff here. Spelling mistakes, okay, maybe not so important, but significant deviations from the procedure or significant parts of scope missed, for example, or deviations from the procedure. These are the things we need to be trapping. And if we write our procedures with a clear verification checklist in mind, that actually could help us to do all of our work, including our verification, very much more efficiently. And this is something I would like to see the industry move towards. So I'd like to take a specific example now. Imagine we've performed the PHA, Process Hazard Analysis, part of our functional safety life cycle. And maybe we did that using a HAZOP procedure, which I expect many of you will be familiar with. How could we do a verification of a HAZOP efficiently? Well, on your screen now, I hope you can see two boxes, a green box and a brown box. Now, in the green box, it says how we can make it efficient from the point of view of the procedure. So let's look at that. The procedure I think it should have a section on verification. It should say, in order to verify this HAZOP study, the assessor should confirm the following. And here's some of the things that I think should be confirming. The first one is, did the HAZOP cover the required scope? somewhere way back at the beginning of the life cycle, there will be a definition of what process scope is included. So for example, let's say it includes unit 100 starting from the battery limit, but not unit 101 and not utilities and not this and not that. And the assessor should be able to check, did the HAZOP cover the same scope as the functional safety life cycle? That should be a very easy task. But very often, the way the documentation is written, it's not clear. It's not easy to find out that information. So that's one thing we could do a lot better. And I have seen HAZOP reports for functional safety life cycles that did not include all the necessary scope or could not be confirmed to have included. And that's very important, because that means we might have missed some of the important risks that we're supposed to be protecting against. Secondly, what are the key steps of the procedure that the HAZOP team should have been following? In other words, what deviations are they supposed to consider? What kinds of scenarios are they supposed to consider? For example, sometimes our HAZOP may say we must consider control loop failures, but we do not have to consider, let's say, hand valve misoperation. So an operator goes into the field and accidentally turns valve A instead of valve B. Should the HAZOP consider that? Some say yes, some say no. If that is clearly stated as part of the verification requirements, then it's easy for the verifier to check just by reading through the list of scenarios, the list of causes that have been covered in the HAZOP report. Did they cover what they were supposed to cover? Did they cover any additional items that are not required? Because those then can be ignored in later parts of the life cycle and don't have to be considered further, because if we do consider them, that might mean that we are overestimating our risk. So that's one thing. The procedure should say what we need to verify. Secondly, and what hazard scenarios to cover. Okay, that's already there. Also, maybe other aspects like what safeguards are we going to allow? For example, are we going to take credit for single check valves, or do we only take credit for double dissimilar check valves? How much credit can we take for relief valves and things like this? Again, all of that, if it's clearly written down as a verification criterion, the verifier can very easily and quickly read through the report or the HAZOP worksheet and say, yes, that was done correctly as per procedure. So much for the procedure. Now, what about the HAZOP report? This is now looking at the brown box on the right-hand side of your screen. Here again, we've got a lot of scope to make life easy for the verifier, to allow him or her to do the work very quickly and efficiently. So here are some of the issues that should be easy to verify. First of all, input documents. We know what the input documents should be, so let's have a list of them, which we can then cross-check against the functional safety management plan or wherever else it's written down, just to confirm that all of the correct documents, including the correct versions of documents, were indeed used by the HAZOP team. Secondly, which procedure was used? Let's have a reference to the procedure document, and again allows us to check that the correct version was used. Personnel. Now, one of the things we do need to check is, are the people who did the safety life cycle step actually competent to do so? Can we look at their training record and their experience record to confirm, for example, that the HAZOP chairman really knows what he's doing and really knows how to chair a HAZOP? That's very important, and that's explicitly stated in the functional safety standard as a requirement. And once again, if we have some very clear lists of who was involved in the HAZOP from beginning to end in the report, that's easy to verify. Now, another thing is, of course, from the functional safety point of view, the main purpose of doing the HAZOP is to identify which hazards may need to have a SIL-rated safety function. So why don't we have in the HAZOP report a table showing all of those scenarios, and only those scenarios that may require a SIL-rated safeguard, a SIL-rated safety function to reduce the risk, instead of having them buried along with hundreds of other scenarios in the HAZOP worksheet. If we had such a table like that, which would be very easy to generate, include it in the report, then all that the verifier has to do is just to cross-check against the main HAZOP worksheet that all the relevant cases are included in that table, and it's done. That would just be the work of a few hours at the most, maybe even less if you've got some smart software that can filter out the relevant cases. Finally, it's critical for this purpose that the HAZOP report uses the full reporting methodology. As you may be aware, HAZOP can be done using either full reporting or a different technique called report by exception. Now, report by exception means any case that either the team could not find a credible cause for a particular deviation, or the team did find a cause but could not find any significant consequence, is not documented in the HAZOP worksheet. Now, that's no good from the point of view of verification, because that means the verifier cannot confirm that all of the necessary scenarios and all of the scope was covered, because some of it is missing. So from the point of view of functional safety verification, you must use full reporting. I know it takes a little bit longer, but with a good scribe and good software, it actually doesn't really take much longer, and it adds a lot of value to the documentation. Right, so that was my views on how we could do verification of one particular life cycle step more efficiently and effectively using a particular case of HAZOP. So let's step back again and think about more generally, how could we actually practically implement a verification activity? Well, my suggestion would be, first of all, let's have a checklist. When we're writing our verification procedure as part of our functional safety management plan, or better still, as part of the HAZOP procedure, let's generate a verification checklist showing exactly what the verifier needs to check to confirm that the step was done correctly. There's no need to write a full-blown textual report for verification. All we need is a checklist to show what was checked and did it pass or did it fail the check, and if there are any open questions or any fails, we need action items from the verification which need to be closed out before we proceed. One thing to consider is when we're doing a verification, if we find issues, we don't have to treat them all with the same level of seriousness. For example, if we have a very small issue, like maybe a document reference number which seems to have maybe just 2 digits swapped around, okay, we can still obviously tell which document was meant, so it's not a big issue. We should correct it, but we don't have to stop the whole show because of that. So you might describe that as a trivial issue. Or maybe we've got a slightly more significant issue where there's a missing reference number, so we can't actually check a document because we don't know which document it's referring to. But that's something that can be quite easily fixed, quite fast, and then the verification can continue. There's no need to stop everything because of that. On the other hand, if we find a major issue, like the procedure was not followed correctly or part of the scope was missing, then we have to stop. We have to stop the verification and we have to stop the life cycle. And we need to go back to the original team that performed the life cycle activity and say, we have a problem, looks like this needs to be fixed before we can go any further. So I'm suggesting we categorize the level of seriousness of the issues that we find. And so we should have some kind of categories defined, and I would think that categorization belongs in the functional safety management plan. You may be familiar with a concept like that if you have done validation before, because you need a similar kind of thing for validation. That is all I'd like to say about verification. So let's move on to the other V, which is the subject of today, and that is validation. In the context of functional safety, validation is a review of an already built and already commissioned safety instrumented system. And what we're trying to do is to cross-check it against the specification. Now, the specification should be defined in a document called the SRS. Now, SRS stands for Safety Requirements Specification. And if I just flip back a few slides into the safety life cycle, you can see I wrote Safety Requirements Specification as the last of the green phases. That's the risk assessment or the risk evaluation phases. So that at that point we should already be drafting an SRS, and then it gets finalized a little bit later on during the detailed design phase. So there should be already a very clear SRS in place for us to cross-check the as-built system against. If there is not an SRS, we really have to insist that some kind of clear, unequivocal specification document or set of documents is provided. Otherwise we can't validate. We have to have something to validate against. Validation is part of the commissioning phase, as we mentioned earlier. It will come after practically everything else has been done. So the system should be all ready to go. Maybe just a few final adjustments to make, but essentially everything needs to be complete by this stage. And it would be just about the last thing we do before the functional safety assessment or pre-startup safety review. Validation normally needs to be done only one time in the life cycle. However, if we make significant changes later to the safety system as a result of a management of change controlled activity, we may need to revalidate the parts that were changed. Now that revalidation can be very specific in scope, so that can be a very small and quick task, and it will certainly be made easier if we had a very clearly written validation procedure and validation report from the first time round, because then whoever is doing the revalidation, maybe 5 or 10 or even 15 years later, after most of us are already long out of the picture and working for other companies or already sitting on the beach with our feet up because we've retired, they will still be able to make sense of what we did and to perform their revalidation very efficiently. Validation needs to cover the entire safety instrumented system. We cannot do it by random sampling. We cannot say we will test 1 out of 10 safety functions. We have to test absolutely everything individually. And the SRS should be our reference point. Now the SRS, as per IEC 61511, at least as per the old edition, the 2003 edition, as you may be aware there's now a new edition just coming out. The old edition had 26 requirements per safety function that the SRS needs to have. I think the new edition maybe has added 1 or 2, I'm not absolutely sure about that. Okay, what does validation involve? Well, various people may give you different perspectives on this, but this is the way I look at it. 2 major tasks that have to be performed: testing and inspection. Testing is basically where we run through every function that the SIS, the Safety Instrumented System, is supposed to perform. So every kind of trip, every reset, every override, I'll give more examples in a minute. We actually make it jump through all of its hoops to prove that it does what it's supposed to do. The other thing is inspection. Now inspection is where we actually go and look at all of the equipment in the field, all of the sensors, all of the valves, the actuators, the solenoids. We look at it and confirm, did they actually install the correct equipment in the correct location, in the correct orientation? For example, if something is supposed to be facing upwards, but they installed it facing downwards, or the direction of flow is supposed to be left to right, but they've installed it the wrong way around, right to left, that could be a problem. Did they actually install the right equipment? For example, if it's supposed to be a rose mount, but they made a mistake and installed some other brand of equipment instead, that would be a problem, because now the SIL verification calculation may not be valid. Is the correct tag number showing at that location? Maybe two devices might have been switched round by mistake. And is the equipment actually energized, and is it actually connected to its power supply, to all the other utilities, and are the connections properly made with the correct polarity, and the pressure is set correctly for instrument air, and all of these things. So we need to actually walk around with a clipboard and get the guys to show us everything as that it is as built. Now this might be a problem if the insulation is already in place. So it might be worth trying to get some of this done a bit earlier before insulation goes on. Otherwise we might have to start asking for insulation to be removed so that we can check. Now another activity that is sometimes considered part of validation is a documentation review, where people say, I want to see that, for example, all of your action items from HAZOP have been closed out. And I want to see that any action items from verification has been closed out. And I want to see all of your procedures and all of your documents are properly signed off. And I want to see that you've got your operating manual ready and all the rest of it. Of course, that needs to be done. But I don't see that as part of validation myself. I think validation is purely a review of the as-built system, the hardware and software, of course, against the SRS. To me, documentation review belongs as part of the functional safety assessment. So I would personally tend to separate those items, but I guess that's a matter of opinion. Right, let's look at a little bit more focus now at what happens during validation. So first of all, the testing phase. We certainly need a checklist. And it's going to be a very, very long and detailed checklist. So preparation is important here. We need somebody who knows what they're doing to sit down with the SRS beforehand and basically convert the SRS into a huge checklist, and it will be huge, of items that need to be confirmed during the validation testing. In my experience, when we're actually doing the testing, we can get through about 4 or 5 functions per day. So it's a very, very big task. Now maybe once we get efficient and we speed up, maybe 6 to 8 functions per day, but do not underestimate the amount of time and effort that this will take. And if you can get yourself a good checklist to begin with, that's certainly going to make things a lot more efficient, rather than trying to write everything down on bits of paper or type it into a giant Excel spreadsheet or something as you go. That's really going to make things more difficult and slow things down, and you might well end up missing important tests, so then you have to come back again later and fill them out. What kind of things need to be on the checklist? Well, here are some examples. We need to check that the sensor trip behavior is correct. For example, does it trip at the correct set point? Does it trip in the correct direction? So if it's a high or low trip, does it actually trip as the process variable transitions from low to high and not the other way around? If there's supposed to be a delay time before trip, does the delay time work correctly? If the trip is supposed to be auto resetting, mostly they will not, but in a few cases you want auto reset trips. Does that work correctly? And perhaps more importantly, does it not auto reset if it's supposed to not auto reset? That's very important. If there is voting on the sensors, let's say for example 2 out of 3, does that work correctly? So you need to try all the possible combinations of the sensors. Or maybe not all of them, but at least enough that you can convince yourself that the voting is working. To test all of the combinations will probably have been done already during the FAT, at least from the software and the I/O card point of view. So there's probably no need to test exhaustively every single combination with the field equipment. Though of course the more you can do, the sounder the check will actually be. So that's the sensor. Now we also need to confirm that the final elements work properly, and mostly what we're concerned with is here, do they end up in the correct state, and most importantly, do they achieve it within the time limit? Now this is particularly an issue if you've got very large valves that need to transition. So that's important to check, and that's a good reason why you should not set your time limits too short. Don't set them really short if you don't have to from a process safety point of view. Every safety function will have some kind of reset function, so check, does the reset function work? Does it do the correct thing? Manual trip. Manual trip is optional, but if you do have, let's say, a hand switch to trip a safety function manually, does it work? Degraded operation. If we have, for example, a 2 out of 3 sensor group, and one of them fails, the system should be configured that it will fall back either to 2 out of 2 or to 1 out of 2. So you need to confirm, based on the information in the SRS, what configuration does it actually fall back to, and does that match the specification. Bypasses. If you have, for example, maintenance overrides or even operator, please don't have operator overrides, but if you do have, maybe you need them for startup, things like that. Do they work? If they have timeout, which hopefully they do have an automatic timeout that clears the bypass after a preset period of time, does that work correctly? Is there a clear indication on the HMI of when a function is bypassed? If there are restrictions on bypasses, maybe let's say you're only allowed to bypass one function at a time, or maybe only one sensor at a time. Does that work correctly? Needs to be tested. You need to test everything in the HMI relating to the safety function. For example, any associated alarms, any associated displays, like tripped or not tripped, and the exact cause of the trip. Need to make sure that works. Operating modes. If you have different operating modes defined, sometimes the safety function is supposed to work in some of them but not in others. So you need to try to simulate that and make sure that that works correctly. Password protection. This is an important one. The operators should be limited in what they can change. They shouldn't be able to, for example, bypass safety functions without a password. And they shouldn't be able to change set points or change logic of safety functions without a password. So make sure that what should be locked is locked. Power up behavior. This is quite important. When you first power up the logic solver, does it go into a defined state? Do the sensors, do the final elements go into a defined state? This is important because what happens if you have a power dip or a power blackout? And when the power is restored, you want to make sure with confidence that your safety system is going to bring your system into a safe working condition and not an undefined condition. There are many more things you need to check. I just wanted to give you some examples. Right, so you can see by now this is going to be a huge and very time-consuming task. So how can we do it efficiently? Well, I already mentioned preparation. Must have a procedure, must have a checklist, very important, must have all the resources available and have full cooperation of the design team and the operational team. And we must define, we need to say we're going to sit in the control room on Monday the 10th of April and we're going to start this validation. No ifs, no buts, that's what we're going to do. And everyone needs to agree. Otherwise, time will slip, people will not show up. There'll be all kinds of reasons why you can't start. You've got to really get the team very focused and the entire team focused on getting this validation done. Once it's validation day, you need to have a lead person who is actually controlling the whole validation activity, and this person needs to be experienced. This is a very challenging role actually. This is like HAZOP chairman plus. So really do not underestimate the difficulty and the importance of having someone who knows what they're doing sitting in the captain's seat, and he or she for this purpose will be sitting in the control room leading this. And you're going to need to have walkie-talkies, people out in the field, people in the control room, people with documentation available. That person has got to be able to control and manage the whole team and to know what to do if you hit a problem, whether to stop and fix it or whether to just continue and let someone work on it while you continue with some other part of the task. Of course, you will have a procedure for the validation, and this needs to be followed to the letter. You cannot be skipping around or bypassing activities or saying, oh, I guess it'll do, it's good enough. You really, really need to follow that meticulously step by step, because when you come to write up the validation report afterwards, anything that was missing, you will find a black hole in the report, and you'll not be able to close it out. You'll not be able to pass the functional safety assessment. So for that reason, you've got to make sure that the results of the validation are really carefully, meticulously documented. This is a really difficult task. I know, because I've done this. Ideally, have a full-time scribe who's dedicated to this. That scribe is going to get very bored, because most of the time they'll have nothing to write. But the trouble is that when they do have, there'll be a flurry of activity. There'll suddenly be 10 results come in very short time. The scribe's got to be able to quickly capture all of that in the checklist without wasting the time of the chairman or someone else or the lead assessor to write those results down. What happens when things go wrong if you have a test failure or an inspection failure? Well, similar to what I said about verification, before you start, you need to define categories of failure. Now, normally I work with 7 different categories actually for validation, and some of them are complete showstoppers. When we hit a certain kind of problem, we say, no, we're not going to do any more. We have to stop completely until this is resolved. Others of them may say, okay, that needs to be fixed, but we can, while it's being fixed, we can do something else. Or another issue would be, yeah, we found a little issue, just a small problem, maybe the wrong color on the screen or something like that. We'll make a note of it. It needs to be resolved, but we can still proceed. And it really helps if you define those kinds of issue beforehand so that you don't have arguments about it in the control room during the validation activity. Right, there we are. So that was our quick tour through verification and validation. So here's my kind of take-home message from today. First of all, hopefully by now it's clear that verification and validation, both extremely important activities, but completely separate. Different kinds of activities done by different people at different times. Verification, now these are both important, but validation people tend to be fully aware of, and that usually does get done to some extent. Verification, I'm afraid, is usually skipped and ignored. And I think this is a problem, because it's a great opportunity to catch errors that might remain hidden in the system for years and years, or even show up later in the life cycle during the, for example, the during the implementation phase, when it's going to be much more expensive to resolve them than if they had been fixed earlier on. So I do really beg you, when you're doing your life cycle activity, do not ignore verification. If you do it efficiently, it takes very little effort and it can give you a big payback. Procedures are very important for both of these. If you're not sure about how to do them, then please contact us and we'll be only too happy to help you with our experience. And we have some template procedures that you can use. And all of this verification validation activity is made much easier and more effective if we plan it in right from the very beginning. From when we write the functional safety management plan, that's when this should be starting to be planned for, and we should be designing these activities at that time. That is the end of everything I have got to say. So now it's over to you. I'm happy to take questions. So please go ahead and unmute yourself. At the moment, I think we have everybody muted, but if you would like to ask a question, go ahead and unmute your microphone, and I'm happy to take them. Alternatively, if you don't want to ask a question at the moment, but you prefer to email us or discuss with us afterwards, then feel free to go ahead and do that.